It's basically running droplets of photo curing materials onto each other and then curing them as it goes along.
Fantastic. Yep, that's pretty much what it is. All right, so we're going to talk a little bit more in depth about that. I think a lot of this is going to be kind of a refresher, but hopefully you guys learned something. So who am I? So I'm Saul. I'm a senior mechanical engineering major. I work at Terrapin Works. I've been running this machine, the Connex, also known as the Objet 500 Connex 3. You can call it the Objet 500 or the Connex. Both are fine. I've been running for about 2 years as a super user. So not only do I run prints on it, I also run maintenance. I train other people how to use this machine, and then I consult with researchers how to best utilize its capabilities. I also love cats, which is irrelevant to this lecture, but I thought it was worth mentioning because it's a big part of who I am as a person. So as an overview, we're going to talk about the Polyjet 3D printing process. A lot of you are familiar with it if you went to lecture or watched the lecture online. We're going to go over it again. We're going to talk about some of its advantages and disadvantages. We're also going to go over the materials that are involved in the process, right? The photo-curable materials that your classmate mentioned that are then UV cured. Design considerations for the specific type of 3D printing technology, right? Every kind of method has its own things that you can do and can't. We're going to go over the ones for Polyjet, and then the printing process in terms of what it's like for a Terrapin Works employee who gets your file, what they have to then do to make your print a reality. So Polyjet printing, it's very much like an inkjet printer, except way more expensive. But ultimately, the technology is very, very similar. I think HP actually came out with a Polyjet printer very recently. So you just have these photocurable layers.
But instead of jetting drops of ink, Polyjet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape.
Right, so you can make all these really pretty parts, very complex geometries with multiple colors. It's great. Here's what it looks like in real life. So we took a GoPro, and then we just put it inside of the printer while it printed with the cover closed. Right now, this is printing a microfluidically controlled soft robotic hand. This is for one of the groups in Dr. Sochol's lab. It's really, really cool because essentially, if you wanted to make all of these different components, you have the little actuators, which are like bellows that will inflate with fluid, causing the fingers to actuate. And then you have these microfluidic transistors, which have different gain depending on how they were designed. And so all of these are printing as one component. So this is a very powerful thing about this technology, is that you can print things that are multiple stiffnesses all at once, and then just clean them by soaking them in a bath, which we'll get to a little bit later. So there's two Polyjet 3D printers at Terrapin Works. There's the Objet 30, which is the baby brother of the Objet 500. We're not going to be talking about it at all, though. We're just, well, very briefly we will be, but for the most part, we're going to be focusing on the Objet 500. So it has a slightly smaller build volume, as is indicative by the number. The number doesn't correspond to the build volume, but if you want to remember it, Objet 30 is smaller. It has a slightly higher resolution. The reason for this, I think, is because the gantry mass is smaller, and so they're using similar motors, and there's less mass, so you have a greater control over it. Because just less play in the whole system. The issue with this printer is that you can only do one model material. So you can get a really high resolution, but in only one material. So you can't get some of these crazy parts that are floating around right now. And this machine is located in TAP. Just to reiterate, you will not be using this for your projects, but it's good to know about as a resource on campus. So this is the one that you will be using. It has a much larger build volume. It can do multi-material mixing and has a resolution of 16 microns. So effectively, the resolution is more 200 microns, which I think was mentioned in the previous lecture. But ultimately, it's advertised to be 16. But you should really design for 50 to 200 micron. So you can make little bits, little tiny bits. Some of the advantages for this kind of technology is that you can print multiple colors in one print. So just an explanation of what these little pallets are. At the corners are the actual material that was loaded into the printer as the stock material, so to speak. So for this one, you've got Vero white at the top, Vero yellow, and then Vero cyan. And then unfortunately, fortunately, it used to only print with these specific gradations, right? Where you could get, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 sort of gradations between two different colors, and if you load a third one, then you have this nice little palette. Now they've updated their software so you can actually have like more or less RGB numbers of colors, which I think is like 16 million, but effectively it's a little bit less. But essentially what it does, right, is you start with these 3 base colors, and then it just combines, it mixes the proportion of each color in the droplets that are being deposited in order to get these different colors coming out. And then furthermore, you can get really, really complex geometries because of the nature of how it prints, right? You have these droplets, they're all being supported with the support material. The support material is then removed, and you are left with these very, very kind of fine, detailed geometries. Some of the disadvantages of the rigid Vero material that you guys are going to be dealing with is that it's rather brittle. So I don't recommend doing this with any of the palettes, but you could very easily just like snap them. They're not really impact resistant. If you wanted to, I was using a Connex print actually over the summer for some research that I was doing, and we had like this mount for a camera that was about this long, it was about this thin, and it was just kind of holding a camera, and we left it for like 2 weeks. And unfortunately, the creep of the material was such that it started off as completely straight and then was like bending after like 2 weeks. So mechanically, it's not great. It's really good for just like demo parts, but not for like final products. And then the flexible material, Tango is the old material that you guys used. The new one is called Agilis. It's very, very similar, except it tears a little bit less easily, but it still is subject to tearing. So even though it's very flexible, if you just kind of get like a nick in it, that nick will creep and it'll tear. Another thing that you can't do with Polyjet 3D printing is have completely closed cavities. So if you think about the technology itself, right, you start off with like a base layer and then you kind of build upwards. If you have something that's like a sphere that is completely hollow, then all of that hollow space that you designed for will actually be filled with support material. And because it's closed off, it'll be impossible to remove, right? So you'll just have this ball filled with support. And unfortunately, the cleaning process is such that you expose it to water, either through water jet or you put it in a sonicator. And the material's a little bit porous, so actually the water will get inside of your sphere, cause it to expand a little bit, and then you'll have a cracked, filled part with support. So you really can't have any closed cavities. Health concerns, so these parts are all super toxic, so don't touch them. I'm just kidding. No, they're totally fine once they're cured. The material before it's cured is actually very, very toxic. So this is photocurable material. The MSDS is real scary. If you want to, like, it's a good Halloween read I'd recommend. If you just like want to be terrified by some of the stuff that you handle like on an everyday basis before it's cured, it's not great. But after it's cured, it's totally fine, ostensibly. Some of the other materials that you won't be using, but the Connex can actually print. It can do transparent rigid materials, which are really nice. So general purpose ones that are a little bit stronger than the Vero Clear. It can do simulated polypropylene, so that again is a little bit stronger, a little bit tougher than Vero. There's also some medical grade materials, so, such as Med 610. So these ones like have they have met the standards for certain like certain benchmarks. So basically, like you can grow cells on them, and the cells won't die immediately. Some of them are okay for dental implants, so that's something that some dentists and orthodontists work with. So the kind of range of materials that are available to print on this machine is always expanding, and they have like very specific material properties that are good for certain purposes. What's up?
Transparent rigid, it's showing a glass. Is it safe once that material is cured to drink out of that, or is that something that you wouldn't necessarily recommend?
I wouldn't recommend it. If you handed me a drink and that drink was at a Connex part, I'd probably turn it down. I wouldn't. I think you might. So if it was from the Med 610, then you're okay, right? Because it has no like toxic leaching, so it's okay for like biomedical research. I think even some of these are implantable into the human body. But for like the transparent one, the glass one, I wouldn't drink from that. Great question. And if at any point during this lecture you have any questions, feel free to raise your hand. I'll get to you as soon as I can. Cool. So some of the material properties, right? You guys are engineers, mostly mechanical. I assume all mechanical. Is that right? Okay. So you want to know the material properties of the things that you're designing with. So I made a chart for you guys of all the materials and their material properties. You can find it at terps/TW materials, and then. Here's some of the just a snapshot of that. So The Veros all kind of have similar material properties, right? They're all right over here. The Vero Blue and the Vero Clear are a little bit different, but they have like a Young's modulus of like 2 to 3 gigapascals, so they're not like super great. Nothing like steel or aluminum, obviously, because they're just like photocurable plastics. But this is a resource that's available to you, so if you want it, go ahead and write down this short link, and it's all yours. I'll give you guys a few seconds to do that. All good? Okay. So Vero is the rigid material. It's got a bunch of different colors, right? We explained these palettes already. Any more questions about this material because you're going to be designing with it? That's what the slide's really for, to field some questions. No? Fantastic. Here's some examples, right? You can make cheap, custom, mostly showcase prostheses. These are not load-bearing materials, but if you wanted to like make them really fancy for like a child, so that the effect of the prostheses is more psychological than mechanical, this is a great resource to use. Just a side note, for prostheses, the psychological component it's probably more important than the mechanical component, especially for children. So that's something to keep in mind if you want to 3D print with Polyjet in the future. If you want to just prototype and then present to stakeholders in your company, this is a really great resource to use, right? You can create these custom-fitted athletic parts that look really great. If you wore a crash helmet at a Vero, you would probably die. So don't do that. But if you wanted to like show off all your new designs, this is a great resource. And another great thing is if you do FEA on some parts or some tools of yours, then there's softwares that allow you to take those color gradients and then map them directly to your print, right? So instead of showing a slide that demonstrates, oh, look, here are the maximum stresses, you can actually take out the part itself and say, here are the maximum stresses. It's kind of cool. And then Tango. So you guys are going to be using Agilis, but the same thing kind of applies, except for the joke, so sorry about that. There's 2 forms of Tango, the black Tango Black and Tango Clear. They act the same. You can form a waterproof seal with it, which is kind of neat. The issue is that it kind of tears easily, as you can see on the picture on your right? So that print is a little tablet that has a mix of Vero White and Tango Black, and you can see that the Vero White has snapped a little bit and the Tango Black has torn. And so those are kind of the two weaknesses of the material. Again, anything for Tango really applies to Agilis. Agilis is just like a little bit improved version of Tango. So if you wanted to make like car wheels for robots for ENES 100 because you want to do college again, right? Wasn't that great? You want to repeat? Me neither. If you wanted to do custom-fitted athletics, again, you could mix this with Vero, and then you could have like a soft part of your helmet, for example, that would kill you, and then a hard part that wouldn't absorb shock. And then this thing I found, it looked cool. I wanted to show you it. Clearly, this doesn't conduct any electricity, so I don't know why anyone printed it, but it's kind of funny. The biocompatible material is really interesting. So Med 610 is used in Dr. Sochol's lab. It's used in Dr. Bruck's lab. It's used in Dr. Yu's lab. It's used by a lot of labs in the bio department. It's really cool because it has medical approvals for cytotoxicity, which means that you can grow cells on it, genotoxicity, which I don't know what that means, delayed, and then a couple of other things that are great and useful if you're doing cell work. And then also, again, like I said, you can use it for dental products. You can use it for dental implants. You guys talked about SLA already, right? Yeah, so also SLA resins are also being approved now to be used for similar sort of dental implants. So it's a bit of a crossover technology, Polyjet is. Then there's a high-temperature material. High-temperature material is a bit of a stretch, right? So what you can get up to, like, from the Connex, like 80 C, right? So it's like not really that high temp. If you tried to like boil it in water, it would fail. So I don't like the fact that they called it high temp, but if it's better than Vero, because Vero fails at like 60 C, so you get like another 20 degrees, which I guess is useful. So if you wanted to test certain things with it, this is a good resource just to know about. The support material. So can anyone tell me? Oh, so these dates are probably a little off because that seems like tomorrow. Can anyone tell me about the support material?
It dissolves in water.
That's correct. What else about it?
flexible, I guess, sort of.
Not quite. It's very brittle. How about where does the support material go? For example, like
Every single anywhere there's a cavity.
Space.
not quite. So it can. So there's two modes on this printer, right? There's matte and glossy. Did you guys talk about that? Okay. So for example, if you look at this part, I don't know how well you guys can see it. Hopefully, very well. Ooh, yeah, duck cam. Let's make it happen.
Be a button on the bottom.
Bottom right.
Bottom right.
Bottom right, document camera. Hey, this is great. Okay, so it looks like here is perfect. Okay, so here's a part. Let me just like rotate it. I don't know if you guys can see this very well. It looks pretty clear. There are two surfaces that look significantly different than the other surfaces, and they're antipodal, right? So there's this surface, and on the exact opposite side, there's this surface. So anybody willing to tell me the orientate, based on those two things, a slightly shiny surface, and I'd say a more shiny surface, could you tell me the orientation of this print?
Shiny down.
More shiny down, okay, that's a good guess.
I'd say shiny towards the sides because it wouldn't need support.
Interesting, shiny towards the sides. So something like, so I think geometrically, that's running against you, right? Because that shiny surface, so that's
Shiny on top.
shiny on top. Shiny on top is correct. Okay, so here's why. So this was printed in, can anyone tell me? Glossy or matte?
The one where there's only support materials up on the underside of the
That is the best answer. Yeah, so that's matte. Sorry, that's not right. That's glossy. And the reason for that is because when you print in glossy, there are surfaces that you can get that are in turn glossy, right? And so basically how this worked is we have this print, right? All of the surfaces that are overhanging are covered in support, and then all the ones that don't have any overhang don't have support. So this is, can someone raise the airfoil? There's an airfoil right over here that exhibits the same thing. I think it's this one. So this was an airfoil printed for the aerospace department because they wanted to do some like scale testing in the wind tunnel. But the issue is it was really important for them to have it such that they didn't have support where like they could minimize the amount of support because there's a bunch of complex geometries that they were worried would break in the support material, the support removal process, right? And so they printed it like, they didn't print on this one, but what they ended up doing is printing it like this. And so that way, some of the internal supports, or some of the internal features, certain faces wouldn't have any support when they printed it in glossy, which is very clever. Yeah, let's switch back to the lecture. Doc cam, top left, room PC. You guys are the best. So how do we feel about printing with cavities? Is this something that we want to do or something we don't want to do?
We can just, depends on if they're closed off.
Approach carefully.
Ooh, you guys are close, but the answer is do not print cavities. So here's the thing. If you print a cavity, right, let's say here's the print bed, here's your part, and then you're like, oh, I'll just have like a little hole over here. It's fine, right? Because we can just water jet. The water will kind of come in. Here, let's give it some support, right? We got a bunch of support. The water is just going to come in, right? It's going to knock the support out, and the support and the water will kind of come out together, right? Right, and that'll be fine. It's not going to be fine, guys. It's going to be real bad. This happens every year, and I feel like I just need to keep stressing it more and more and more. Do not have cavities in your print. If you could call it a cavity, no, I wouldn't go that far. If you can't get into the hole that you've made into your part that leads to an even bigger hole with your like smallest finger or the smallest finger of the smallest person on your team, you're doing it wrong. It's a nightmare to get out this support material. So just please avoid it at all costs, especially if it's a small part. Because if it's a water jet, you can sort of maybe do it, but it's really, really annoying. But if this part is like real small, like if this is like the size of like something on your nut, like just the size of like a knuckle, then the issue is you're going to have to sonicate this. And the way sonication works, if you guys remember, is the caustic solution that dissolves away the support material can only interact with the material that it's physically touching, right? So that means that the caustic material will only eat away here, and then eat away here, and then eat away here. And so it takes like 3 days, and then your part's all gross, and just don't print in cavities. So I'll ask again. How do we feel about cavities, you guys? Garbage. Yeah, that's what I want to hear. Okay. So I don't want to see any cavities in Terrapin Works. Thank you. So let's this is where it gets cool, right? So you have this rigid material, you have this flexible material, but you can combine them, right? So how many of these are floating around? I have one extra. Who wants to catch one? You want to catch one? Hands first. Cool. Okay, so everybody who has one, raise it up. You got like two. Can you, or is that, you just have one? Okay, great. So if you look at the one that looks like the most of one color, that's next to the one that's like the farthest away from it, right? So in my case, it's totally white and totally clear. For you, it's totally black and totally white. The totally white one on both palettes represents, so here's a little different, so I guess just like, come on for the ride. The totally white one is all Vero clear. Sorry, that's not true. It's all Vero white. And then the totally flexible one for you is Tango black, and for me is Agilus 30 clear. And then everything in between is a combination between a varying ratio between Vero white and then Agilus for me and Tango for you, right? And so this kind of gives you an idea, and this is actually super important for your project. Make sure that you get a hand on this. If not now, then you come to TerraPlanWorks, because this will kind of tell you mechanically, it'll give you an intuition for how it behaves, right? Because you can look up like the shore hardness of this material, but like I don't know how to design for shore hardness. I don't know about you. So for me, it's whenever I design with this material, it's very useful to just kind of like grab this palette, flex it, and then think like, how much do I want my part to flex? Like, does this make sense? So I'll be passing this around. And unfortunately, even though the colors have had an update so you can have like a nicer gradient and it's not so like rigidly incremented, that's not the case for the flexible material. You really have, I think, 10 different options between a completely flexible material and a completely rigid material. So some really cool multi-material examples. This is a liver on the left. Here, I'll pass this around. This is a liver on the left. It's got all of like the really intricate circulatory liver stuff going on through it that's really good for surgical planning. So if you want to say like you want to attack a specific person, no, that's not what I want to say. If you want to attack a specific problem in a specific part of a specific person's liver, then you could do a CT scan of them, and then you could plan using a model that is anatomically correct to that individual where you're going to kind of start your surgery. This is very particularly relevant for minimally invasive robotics, because then you can make a very small incision, insert your laparoscope, insert like your Da Vinci tools, and do all that cool stuff. So it's a very powerful tool for surgical planning. You can also make custom fitted shoes. I haven't seen anyone really do this, but it was a cool example. They would look cool and they'd fall apart hella quick. And then you could do dental models, again, like if you wanted to show someone what a dental surgery would look to their, like in terms of how it would affect their teeth, like what their teeth would look like at the end. This is a great example. The limitations are really up to your imagination with this technology. It's pretty incredible. We talked about this a little bit. We've got matte, Damon, and glossy. The big difference between matte and glossy, can anyone sum it up for me? Someone who hasn't talked already. We have like, we have so much time. All right, come on, guys. You talked already. Come on, we got it.
Sorry, I was like,
oh, sorry. Okay, so to repeat the question, can anyone break down for me in terms of support material where it goes and where it doesn't between matte versus glossy? Like, what's going on?
Yeah.
You, sir.
Well, with matte, every surface that's printed is covered in support material, even the top surfaces.
Yes.
Wouldn't strictly need it for support reasons, but you put in there for material property reasons and look reasons.
Yes.
And then glossy, it only puts support material where it needs support material. So any surfaces that don't need to be directly supported have this different finish and different material properties.
That's a perfect explanation. Great job. Yep, that's completely correct. So this might be a little bit different. This is just a slide about last year's homework assignment for this project, which is the same assignment, but the way that the files are going to be submitted might be a little bit different. So if this conflicts with anything that you've been told, ignore this and then just go with what you heard before. In general, when you're submitting parts to TerraPlanWorks, we need to know the file type that you're which file is what material, because that's how it's going to be assigned in the printer, which I'm going to talk about in a second. But basically, just have the name of a part underscore plastic or underscore rubber. You could call it Vero. You could call it Agilis. Both. That's also fine. Just make sure that you're delineating or that you're separating between the rigid material and the flexible material in some way in your naming convention. Yes.
So,
Go ahead. You're good.
can we have any combination of the rigid and the rubber, or is it only purely the hard rigid material and then half and half and then purely the rubber?
So that's a great question. That is not up to me. That's a good question for Lena, for Dr. Sochol. Lena, did you hear his question by any chance? Oh, I think she's checking.
No, it doesn't say specifically in the homework that you can or cannot do that. However, it says that you can either use Veroplastic. Actually, that may actually answer your question. You can use Veroplastic or Agilis 30. Agilis 30.
So I would ask Dr. Sochol like specifically because I mean technically you are doing that when you mix them, and it kind of opens up like 10 more materials, so to speak, that you could use. So like if you guys are using Piazza or you guys are using Slack, right? So just like hit them in Slack general, talk general, and just like see.
I would say for right now, don't count on mixing them because when you submit the files, you're going to be submitting them with like whatever parts or whatever materials you're going to do this piece blah material, and that material has to be either Agilis or Vero. So it's not like you do submission this piece and then material Vero 60% Agilis, 40% or whatever. That's what it seems to me. I will contact Dr. Sochol, but for right now, just go with that.
Yeah. If it turns out that you can select it, the way that you would select the material, unfortunately, is not percentage-based, but is like this weird naming convention that strategists came up with, which like makes a little bit of sense, but ultimately is kind of confusing. So if you start off with a flexible material, it's a good way to put this. All right, so you have like, I believe it's RGD is over here, then there's like some arbitrary line, and then there's like FLX, right? So this stands for rigid, right? And this stands for flexible X. I don't know why they put the X there. But essentially, if you have, let's say, Agilis over here, then the thing that's one step above Agilis towards Vero is going to be an FLX thing. And then the thing that's, if this is Vero, that's one step down towards Agilis would be RGD. It might also be DM for digital material. That's what they call the mixing stuff. It's just called a digital material. And so these will have numbers corresponding to, honestly, I'm not sure, but you might see something like DM 9685 or FLX
9740.
9740. You probably wouldn't see, but grade 4 numbers you need.
It's on your keychain.
Oh, it's on. Oh, thank you. Actually, never mind. I'm totally wrong. This is something that you would see. And so basically, if you, I appreciate it. Sorry for sassing you. Instead of saying, hey, I need 40% this and 60% that, that's not really helpful for the Terrapin Works person. It's more helpful to see like, I need this. I need that. Because that's actually what we're going to be selecting in the software, which I'll talk about in a second. Yes?
So in this case where you have like the part underscore plastic, what would you write in the underscore? Those RGD numbers or specific for submitting files?
I'd say to be safe, include the material like this in your file name. Because there's a couple ways it could happen. It could be that you send that information to Lena, and then Lena sends it to us. But that's just more work for Lena, and just include it in your part name, and then in Lena's email, she'll specify like, look, some of these parts have are not just Vero and are not just Agilis, and that'll be specified specifically in the part name, or in the extension of the part, so to speak. Not the extension. That's different.
You guys are going to do your team number. So you're going to give us a big folder, basically, of your files. And you're going to decide which part you want to be one material and which part you want to be another material in the assembly of your part. And then you're going to literally do team name material.stl for each material. And that's how and you're going to put that in a file and you're going to send that to us and we're going to send it to you. So just please make sure you put your team name, you put your material, and I just emailed Dr. Sochol about composition, whether or not it can be a multiple composition. So hopefully he'll get back to us on that.
Great. Any other questions before I move on? What's up?
If it's on a dotted line, is that flexible or is that considered flexible or rigid?
That's a great question. So there is going to be. This is the dotted line is between where it arbitrarily switches between FLX and RGD, right? It's going to be like flexible, rigid-ish. Like I don't know why they chose it. They probably chose it because it's halfway. That's what I would do. But yeah, it's like some mix between. Any other questions before moving on? Cool. All right. So when you design parts, what unit system do you use? There is a correct answer. Millimeters. I want to hear it. I want to hear it loud. I want to hear it proud. SI is the best system in the goddamn world. What units do you use? That was so underwhelming. What units do you use? Good God. Have you tried engineering in inches before? It's a nightmare. Like, come on. What units do you use? Millimeters. Thank you. Oh my God. Inches are garbage.
Unless you're machining.
Unless you're machining. Okay. Unless you're machining, then it's fine.
Just feed and brush the feed into us, like there's no more excitement.
You gotta resist that toxin into your mind, man. You gotta keep it pure, keep it SI. That's the only way to do it. Right. So to do everything in millimeters, make it easy for us. If you gave it to us in inches and you told us we could, but that's like 2 more buttons we need to click, and so like just don't make us do it. That's what it breaks down to. So how do we feel about parts like this solid part?
Solid part's
Yep,
fine.
that's
Solid part's fine, yeah. How about solid part files?
Sure.
No, so what I mean is like this. .SLD.PRT. How do we feel about that? No, right? How we feel about this though?
Oh yeah.
Hey, we feel great about. Ooh, that's not a smiley face. We feel great about that. So how about the part in the middle, right? The one with there's no. It's like totally hollow on the inside. Exactly. Exactly. Why would you do that? And then the second one, how do we feel? The third one, how do we feel about it?
Possible.
Yeah, if you like really have to, and like you hate everyone at Terrapin Works, and you're like, I want to really ruin their day. Cool. Okay, so in terms of orientation, you guys should have already had a lecture about that, like what you're going to consider. So I'm not going to beat a dead horse. Important numbers to consider if you want things to overlap. There's a bit of disagreement about this. I stand by, because like I've experimentally seen it and done it myself. If you have a part like in an assembly file, right, where this is your Vero and this is your Agilis. Agilis. Okay. Then if you just have like them touching in your CAD file, then they will be actually touching in your in the part. Now here's the deal. You guys remember from 220 that if you have like different materials and then you have like an interface, then this is like a weak point, right? Yeah. Right. So there's ways around that you can be really clever and do. It's going to take a little bit more time in the CAD, but something that I've seen, I've implemented successfully is instead of doing something like this, you do something like this. Ooh, that's a bad overlap. Right, because ultimately the failure mechanism for a part like this isn't that the materials, isn't like the strength of the materials themselves, it's the strength of the bond between these two different materials. And so what you want to do is maximize the surface area between these two. So if you're kind of worried like, oh, I feel like this will tear apart, this is a good thing that you can implement. It's kind of annoying, especially if you have like a kind of a weird complex interface, but it works for microfluidic capacitors, if that tells you anything. So does this make sense to everybody? I feel like it's pretty intuitive. Cool. And then if you want, like, you could also make them overlap. That won't hurt you, but I called up Stratasys and was like, okay, so what's the deal with overlapping parts? Turns out the software just looks at the overlaps, is like, okay, that's fine, and then assigns the overlap to either the Vero or the Tango. It just arbitrarily assigns it. Well, not arbitrary. It has like some hierarchy that's embedded in the software, but like you won't know what it is because I don't know what it is. And so it's the same thing as if you had just done this. But that's better, so if you can do that. Also, what file type do we like? Just want to hit it again because sometimes we get the wrong file type. STLs. Does anyone know what that stands for?
Standard something.
Yeah, it doesn't matter, right? But apparently it stands for like standard tessellation language. Like people keep renaming what it means, or like stereolithography file. I don't know. It doesn't matter. So basically, so you're going to send your stuff to Lena. She's going to send it to TerraWorks. We're going to open it up in Object Studio, the worst software in the world.
For real?
What? Oh, well, yeah, maybe.
Dances.
I know you did this.
All right, never mind. One of the worst softwares in the world, and then it's going to go to the printer. So fortunately, we transitioned to GrabCAD Print, so that's a lot nicer software. But I didn't transition these slides because there's exactly the same information. So you're shooting this really nice email. This is more if you were to send your own email to TerraWorks for like your own kind of print. This is kind of what would happen, right? You send an email, it's really well crafted. You're like, hey guys, how's it going? We love seeing that. Not like, hello, TerraWorks. This is this material and this time, and I need it for this lap. Thank you. Like just like jazz it up a little bit, makes your lives a little bit better. So your STL file goes into Object Studio. If you have an assembly, then we'll import it as an assembly. How do you export parts as an assembly in SolidWorks? Does anybody know? So you have like this cool assembly, and you want so you've got like, you've designed like the coolest, hippest new toy. Oh man, you're just so excited. It's like this cup, right? And oh man, but it also has like this ball. Oh, and it's connected to a string. And you want to 3D print it because you're a maniac. This is what I thought of right now. So, but these are all 3 different parts. You have a magical 3D printer that can print string now. And so this is part 1, this is part 2, and this is part 3. So you have it in SolidWorks, right? You're like, ooh, SolidWorks window, ooh wee. How do you get this out of SolidWorks and into 3 separate STL files that, when imported into this software, will be aligned like you want them to? You want this to print as one object. Does anyone know how to do that?
Press tilde 2, you save it as solid part. Well, I guess that's if you're dealing with multiple parts. So they're all different materials. I think you just save it as an STL and check as a save as separate STLs. It's an option.
Yes, that's exactly right. So all you do is you just go into SolidWorks and you click Save As in the assembly file. So don't do it for the individual parts. Save it as the assembly file, but then save them as STLs, and then make sure you click a box that says Save as individual parts. Or you make sure the box that says Save as one part is unclicked. If you don't know, just Google it, right, as anything, as is with anything. But make sure that you do that, because if you just send us individual parts, then they'll just be like random and disconnected. So then we would import them as an assembly. They'd show up as an assembly. It looks great, right? So this is a spatula. It's got like a flexible grip. And then it's got like this nice cool handle. Excuse me. This is what would look like if we didn't import them correctly, right? You got this like tang of the spatula that's all exposed. It's so alone, man. It just wants the nice warm embrace of a handle, but it can't have it because the TerraWorks employee messed up. So then now you have this like nice little model tree. You've inserted the STL. You did placement, then you validated it. That just makes sure that the file itself isn't like busted. And then it estimates the time that it'll take and also the material that will be used. And then you actually send it to the printer. This little thing keeps tracks of the parts. It's not super relevant for you guys. Then at this point, we'd manually select, we'd click on the part, we'd read the part name in the software, right? So in this model tree down here, you would see the part name, and we'd say, oh, this part needs to be like RGD, C, like that, whatever that string of characters is, right? And so we'd select it there. So by sending the material that you want specifically in the part name, just makes it easier for everybody involved, less mistakes, it's just cleaner. We'd also select at this point matte versus glossy, right? So if you're printing parts, so I think you guys are printing parts that are continuous, that are like all one thing, so you can choose whether or not it's matte or glossy. I don't think you can choose it individually for the components because they're printing as one thing. It's probably just best to just choose one over the other. Any questions up to this point about anything I've covered? Cool. Then we can like move it around. We could change the parts material, right, which we talked about, and the color. At this point, we'd send it to the printer along with all the other prints, and then we'd remove it in the post-processing, so either water jet or in a sonication bath with some like caustic solution of sodium hydroxide. And then there's also like options for post-processing, so you could like paint your part and then like put it in your car, for example. I think that's a car part. You could have like you could polish it, so even though the surface finish isn't great, the internals are continuous and like homogeneous, so there's no defects. And so if you just polish the outside, then you get this like really nice sheen throughout your part, which is like quite cool, like this ship in a bottle sort of deal. Right, so Polyjet printing, it's great. Is it great for all things? No, because of its advantages and disadvantages. It's got a lot of different materials. You are constrained somewhat in the kinds of designs that you can do, and then now you guys know how to set up files. So any questions? If you have any, you can shoot me an email. Got the best email on campus, saul@umd.edu. And I'll respond to you, hopefully, pretty quickly. And then if you have any questions that you really need answered, you can go to where the printer is, which is in 2123 Clark Hall. That's the Advanced Fabrication Lab at Terrapin Works, and that's where it's currently housed. Any final questions or concerns? Great. Well, this has been fun. Hope you learned something. Can I get all the parts back? Oh, are you guys going to clap? Well, go ahead and clap. Oh, that's so nice.